So today I'm going to be recording the next installment of this 6036 problem 2D on problem set 6. And where we last left off, we had calculated these two derivatives right here. The derivative of the negative log likelihood loss with respect to AI, and the derivative of these activations with respect to their pre-activations. So those things are shown here, and they're shown here. So the next step is to put them together to get what this derivative of the loss with respect to the pre-activations. So I am going to first get some new real estate. And so what we want is here, let's go a little bit to the left. So what we want is the derivative of the NLL with respect to ZJ, right? Let me just double check the indices. ZJ, yes. And we're summing over the dummy variable I. So equals, so we sum over I of the derivative of NLL with respect to AI times derivative of AI with respect to ZJ. Okay, so we have these two results, and so we can just plug them in. So this becomes sum over I. This is just negative yi AI. If you recall from the last video, we had that result right here. And the other result, if you don't remember, is this, AI times the delta minus AJ. So we can write that here. So this is going to be AI times delta IJ minus AJ. Okay, so what is this? This negative sign can go outside the sum. So we have negative sum over I. And then these AIs cancel. So we just have yi times delta ij minus aj. Okay, we can simplify this further. I'm going to break this sum up into two pieces. So because this sum is distributive. So we can write this as negative sum over I yi delta ij, and then plus sum over I yi, and then we multiply by aj, but notice that aj does not depend on I, so we can factor it out of this sum. So we have aj. Okay, so how can we simplify this? Well, this sum has a sum over a dummy variable where the dummy variable has a Kronecker delta, or there's a Kronecker delta has that dummy variable. So that means that this sum is only non-zero when I is equal to j. So that means we can set I equal to j and get rid of this sum and this Kronecker delta. So this is negative yj. Okay, now let's look at this. So what is the sum over I of yi? That's just the sum of all the different components of y. So if we go up, we can see that y is this vector here. y is this vector here. So the sum of all the different components is 0 plus 1 plus 0. And this is generically true for any one-hot vector. So we know that the sum of all the components of y is just 1. So we can ignore this term. This is just 1. So this is yj plus aj. Or in other words, this whole thing is just equal to aj minus yj. Okay, so we still have a little bit more work to do. We're getting closer. So we just computed this term, and also this term appears in the final expression for the gradient with respect to the weights as this pink entry right here. So show this entry right here is what we just calculated. So that's this thing here. So we have, before we can calculate this one final sum, we have one more thing that we need to calculate, which is this guy here. So we're going to calculate the derivative of ZD with respect to omega, or not omega, WLM, the weights. And so to do that, let's first recall the formula for the weights as a function of the weights as a function of the, or what ZJ is as a function of the weights. So let us write that down here. So scroll down. Okay. So we have, I'll do that over here. So we know that ZD equals the sum over, let's call this dummy variable P, omega W P D X P. So that's what the formula is from above. You can check if you rewind the video if you need a refresher on this. And then we can add this bias W naught. But this won't really matter because we're taking a derivative. This will disappear. So now we want the derivative of ZD with respect to omega. Let me just check the indices. It's always a good idea to check the indices. LM, that's what we want. LM. So we have LM. And so the derivative goes inside the sum, and the constant term vanishes again. So xp is just a constant, so let's just write that here. And then we have the derivative of WPD with respect to WLM. Okay, so how do we simplify this? So this is, each of the weights are independent. Each of the weights are independent components. So this is very similar to the thing we had here, where we were taking something like dZj with respect to dZi, and this turned into a Kronecker delta. The difference is that in this case we have two indices, so both indices have to be equal. So this derivative is only non-zero if P equals L and D equals M. So we can write this as follows: sum over P xp delta PL delta dm. Okay, and so then we can evaluate this sum over the P index, because this P only has support, or this delta function is, or this delta Kronecker delta is only non-zero when P is equal to L. So this becomes very similar to how we've done this before, XL delta dm. Okay, so let's put all of the things together. So recall our formula. So the derivative of NLL with respect to the weights is this final sum here. So we can go down and we can compute this final sum. Okay, let's see. What color have I not used already? We'll do it in pink. Okay, so the derivative of NLL with respect to WLM is going to be the sum over D of DNLL with respect to CD times derivative ZD with respect to WLM. And at this point, it's just substitution. We can substitute this result in here, and we can substitute that result in there. Okay, so what does this become? This is equal to sum over D, and then this derivative is just going to be AD minus ZD. Sorry, I messed up. It's going to be AD minus YD. And then this derivative is going to be XL times delta dm. Okay, so this delta can kill this sum because Kronecker delta is only non-zero when d is equal to m, so we can set d equal to m and kill the sum. So this is equal to AD, oh sorry, not AD, that was the whole point. AM minus YM times XL. Okay, so this is our final answer, but we're not quite done because it's still in this expression is still in the language of indices and not in the language of matrix multiplication. So if we go back up and look at the problem statement, this W matrix is of the form, it has two rows by 3 columns. Excuse me. So, and this is X vector has 2 rows by 1 column. And this Y vector, Y and A, both are 3 by 1. And so how do we multiply a 2 by 1 by a 3 by 1 and get a 2 by 3? Well, if we transpose this, we can get a 2 by 1, and then we can multiply it by a 1 by 3, and this will give us a 2 by 3. Now, if you were to go to Wikipedia and look up the index-wise formula for matrix multiplication, you would find that this expression here is the same as basically the indices work out to be, if we have the matrix representation of X and then A minus Y transpose. And so if you do the matrix multiplication, you'll see that the LMth index is given by this, right? The the rows come from X and the columns come from A minus Y transpose. So I hope you enjoyed this. This is the final answer for our back propagation. So this is our final answer. So I look forward to seeing you in the next video.